My first topic is L'Hopital's rule, a method for determining limits in cases where direct substitution results in an interdeterminate form such as 0 over 0 or infinity over infinity. An interdeterminate form is a mathematical expression such as 0 over 0 or infinity over infinity whose values can't be determined. Here is a chart showing how to apply L'Hopital's rule. Basically, you do the derivative of the top over the derivative of the bottom when you have an expression that is 0 over 0 or infinity over infinity. My example is limit x going to 0, e of x minus 1 over x squared plus x. First, you need to determine if L'Hopital's rule will apply, and in this case it does. Then you do the derivative of the top over the derivative of the bottom. The derivative of the numerator is just e to the x, and the derivative of the denominator is 2x plus 1. Now you can plug in 0 to evaluate, and you get the limit is equal to 1. The next topic is optimization. This is the process of finding an absolute maximum or absolute minimum value of a function. A first derivative test is a test on the critical values of a function to determine whether a local maximum or local minimum exists. Here are the steps to optimization. First, determine what you are trying to optimize. Second, write an equation to be optimized and make sure there's only one independent variable. Third, perform the first derivative test. Fourth, compare your local extrema to the endpoints of your domain. Fifth, conclude and include units in your equation. My example is to find the maximum volume of an open box with a square base that is to be constructed from 108 inches squared of material. What dimensions will produce a box with this maximum value? We know the volume of the box is length times width times height, and so we also can draw a picture to demonstrate this problem. Next, we write a formula for the quantity we are trying to optimize. The formula must be written in terms of a single variable, so we can use a surface area equation. We can plug in 108 for the surface area because this is told to us in the problem, and then we can use this formula to solve for z. Now we can substitute z back into the volume equation. We know the sides of the box must have a positive length, so x is greater than 0. Now we need to take the derivative of the volume equation, so we can first simplify to make it easier for us to differentiate using the power rule. Then we set the derivative equal to 0 to find the critical values. We get x is equal to positive and negative 6. Since negative 6 is outside the domain, therefore only 6 is a critical number. We now perform a number line analysis to determine whether we are going from a relative maximum or relative minimum. We see that it goes from positive to negative, therefore it is local maximum at that point. We now can plug the critical value of 6 back into the volume equation, and we get 108. Therefore, the maximum volume of the open box is 108 cubic inches.